So, over the last couple of days, I asked you to do a deep dive on disorder, how to predict the direction of the disorder, and how to use this to determine if a reaction is spontaneous or not. And one thing that we remember is that reactions are spontaneous when. And this when involves two parts. First off, delta H. They tend to be spontaneous when delta H is negative. That means they are exothermic, and that means they give off energy. They also tend to be spontaneous when they increase disorder, or in this case, we're going to call it entropy. And so we know that reactions that do both of these, give off energy and increase disorder, tend to be spontaneous, but sometimes there are reactions that go seemingly in opposite directions. Let's take an example. We know that boiling water requires energy. You have to add heat. That's that little delta. We know that this is a reaction with a positive delta H. But we also know that going from a liquid to a gas increases disorder. So this should be spontaneous. Well, how do we know? Well, that's what Gibbs free energy tells us. Delta G, let me make this a little smaller so it doesn't look like I'm trying to draw with a monster truck here. Delta G, what we call free energy. And we've seen this before, but we're going to look at it a little differently. This determines spontaneity. And so we'll say this, that delta G has to be less than or equal to 0. And when that's the case, our reaction is spontaneous. So if we're looking at this reaction of boiling water, I mean, you don't even have to really to be a scientist to know that it doesn't happen by itself when the water is just sitting there, but it happens great when the water is above a certain temperature. That means that this reaction is spontaneous only under certain conditions. What are those conditions? Temperature. So let's do this, and let's get some thermodynamic data here. So I'm going to go into table A4, and that's not what I wanted. That's the chapter review. You guys don't want that. Let me get some data. So these data are going to come right from table A4, and we'll put them right here. We're going to ignore the column in the middle. That column is delta G, and we're just going to ignore this column. So delta H, and this is going to be the disorder for both of these molecules. Let's calculate the overall delta H. So we'll use this fancy new equation that we have where we'll say the overall delta H of the reaction is equal to the sum of the delta H of the products minus the sum of the delta H of the reactants. And so, of course, our single product being water vapor will have negative 242 kilojoules per mole, and we're going to subtract from that negative 286 kilojoules per mole. This gives us delta H of plus 44 kilojoules. Makes sense. It's an endothermic reaction, so it should be a positive delta H. Let's do the same thing for delta S of the reaction. We'll use the same equation, and we'll say that delta S is positive 189 for gas and positive 70 for the liquid. So we're going to go from products to reactants, and we'll say, and we should know that this should be a positive delta S. So we'll say 189 minus, and remember this is in joules per Kelvin mole, so joules is pretty crucial, minus 70 joules per Kelvin mole. And our delta S should also be positive 189 minus 70. positive 119 joules per Kelvin mole. All right, so makes sense. Our delta H and our delta S are both positive. So what's the delta G for this reaction? Let's say that we were just going to do it at room temperature. Temperature is equal to 25 degrees Celsius, otherwise known as 298 kelvins. Now you know the answer to this question. Does water boil at 25 degrees Celsius? Room temperature? No. We'll calculate it anyway. We'll say delta G is going to be equal to delta H minus T times delta S. We know the delta H. Let's get these into matching units. So we'll call, instead of 44 kilojoules, we'll say 44,000 joules per mole minus the quantity of 298 kelvins times 119 joules per mole Kelvin mole, and of course we know kelvins are going to cancel. So let's do this in the parentheses first, and we're going to say 298 times 119, and this is 35,462, so we're going to have 44,000 joules per mole minus 35,462 joules per mole. Remember, kelvins cancel. What's our delta G? 44,000 minus this answer, 8,538 joules per mole, not spontaneous. But what if we heated our water to, let's make our temperature 110 degrees Celsius. We know water boils at 100. So will this occur spontaneously? This is now 383 kelvins. So delta G equals delta H minus T delta S. We'll say our delta H is 44,000 joules per mole minus T, 383 kelvins, times our delta S, which we said was 119 joules over Kelvin moles. Remember, kelvins cancels. And so what we'll have is, and this has not changed, this is still going to be 35,462 joules per mole inside these parentheses. I'm sorry, no it isn't. Ignore what I just said, because we're multiplying by a different temperature. So ignore what I just said. Let's multiply by 383 kelvins. So 383 times 119. This is now 45,577 joules per mole. Kelvins cancels. And of course, we're going to be subtracting that from 44,000 joules per mole. So, is our reaction spontaneous? It has to be negative for it to be spontaneous. 44,000 minus 45,577. Negative 1,577 joules per mole. And that reaction is spontaneous. So it makes sense. We know that the reaction is going to be spontaneous over 100 degrees Celsius. How do we set this up so we could just find the temperature? So if delta G has to be less than or equal to 0, let's just call it 0. And that means that if we take this equation, delta G equals delta H minus T delta S, and we set it to 0, delta H minus T delta S, then now what we have is T delta S equals delta H, and that means T is equal to delta H over delta S. So what's the temperature? I think you know the answer to this one. If the delta H for this equation is 44,000 joules per mole, and the delta S is 119 joules over Kelvin moles, notice that this time joules are going to cancel, moles are going to cancel, leave our answer in kelvins. 44,000 divided by 119. Isn't that interesting? This is now 370 kelvins, which is roughly boiling point. All right? Should be 373, but that's what the numbers give us. All right, so this equation is a pretty useful one. All right, so let's take this for a spin. It's going to be a trip down memory lane for a lot of you. And I will see you all on the next one.